So finally now in the third and final chunk of the Lecture 7 series, we're going to actually see chymotrypsin in action. We've given as much setup and as much background as we possibly can, and hopefully we're in a place now where we can frame the context of what's going on in the active site of chymotrypsin comfortably and understand what we're seeing. So we've talked about phosphorylation and zymogens, and we spent a lot of time in the last chunk talking about active sites in general and the importance of three-dimensional space for those active sites, getting side chains lined up properly so that they can work on substrate. And we talked about chymotrypsin specifically as a serine protease and its job of cleaving peptide bonds. We're going to jump right in the next slide now and look at the enzymatic mechanism of chymotrypsin itself. We'll fill in the gaps of chymotrypsin and talk about some other types of enzymatic strategies that enzymes use to perform catalysis, and end with a discussion of coenzymes, small molecules that help enzymes do their job. So let's get started. Chymotrypsin as an enzymatic mechanism. We already know from the previous chunk that serine 195 and histidine 57 are the two most critical amino acids of the enzyme, and both of them are found in the active site. Also, both are reactive, with histidine having a true charge and serine having a hydroxyl group. So here they are. Serine 195 in this schematic is right here. Here is the hydroxyl group of the serine side chain, and histidine 57 is here with its side chain as well. Histidine of course, has an aromatic ring, and that ring contains nitrogens which can be protonated. The first thing that we need to consider is that the oxygen of the hydroxyl group in the serine side chain is a nucleophile. It's an attacking nucleophile, and it's hungry to make bonds. Specifically, it's seeking positive electron-poor groups that it can attack in order to make new covalent bonds. This is as opposed to electrophiles, which you've probably learned about in your chemistry courses. Electrophiles are looking for negatively enhanced proton-poor groups that they can attack. So this nucleophile on serine, this oxygen of the serine hydroxyl group, launches a nucleophilic attack on the carbonyl carbon that's engaged directly in the peptide bond on the substrate molecule. So this group here that we see in the active site is the substrate. In fact, this is the hydrophobic pocket we talked about in the previous chunk, and R1 is the side chain of a hydrophobic amino acid that has been sheltered here from water by interacting with the hydrophobic pocket of the active site. That's the positioning we talked about in the last chunk that brings this peptide bond directly where it should be in three-dimensional space. So here is the peptide bond that we're going to be attacking. This is the carbon of the carboxy group of the amino acid just before the peptide bond we're attacking, and this is the nitrogen of the amino group of the amino acid just after the peptide bond we're attacking. So the first step of this enzymatic mechanism is that the oxygen of serine directly attacks the carbon lying just ahead of the peptide bond. There's the attack, it just occurred. So a number of things occurred as a result of this attack. The first thing that occurred is that oxygen can, of course, only make two bonds at any one time. One of those bonds is holding the hydroxyl group, or what was the hydroxyl group, to serine itself. The second bond we just made is with the carbonyl carbon. Therefore, that oxygen had to let go of its proton. That proton has been absorbed by histidine 57. This is histidine 57's job in the enzymatic mechanism, to serve as a holder of serine's hydrogen. The other thing that occurred is that the double bond that was previously present between this oxygen and the carbon, that double bond we see here, has been reverted to a single bond because carbon can only make 4 bonds at any one time. Since there's only a single bond holding this carbonyl carbon to its oxygen, this oxygen is now negatively charged, and it is not happy. So that carbonyl oxygen being negative and being so unhappy and so unsatisfied is going to launch its own attack. Getting ahead of myself, keep in mind histidine has held on to that hydrogen from serine. And that hydrogen is now making a hydrogen bond with the nitrogen on the other side of the peptide bond in the substrate. Because that negatively charged oxygen was so unhappy, it launched its own attack on the carbonyl carbon, and it is asking for its second bond back. Simultaneously, we have this hydrogen pulling on this nitrogen on the other side of the peptide bond, due to this hydrogen bond between the two. You can imagine that the peptide bond is stuck in the middle. We have this oxygen pulling on carbon on one side, asking for its double bond back, and we have this nitrogen pulling on the peptide bond on the other side due to this hydrogen bond over here. That's too much stress for the peptide bond to withstand, and the peptide bond snaps. Since the peptide bond snaps, this oxygen gets its double bond back, and we see that the proton that histidine was holding has been donated to the amino group, or the nitrogen, on the other side of that peptide bond. This half of the substrate that we see here is now the leaving group. That half of the substrate molecule leaves the active site and floats off back into the environment. Histidine acted as an acid in this case. It donated a proton in this scenario, gave up a proton so that the nitrogen would have the 3 bonds that it needs to be satisfied. So we've broken the peptide bond. The point of this reaction was to break that peptide bond, and it's broken. We're done, right? Well, no, we're not done. We're dealing with an enzyme, and the main rule of enzymes is that they're recyclable, that they end their reaction in the same state that we started. When we started this reaction, serine was made up of nothing more than a hydroxyl group, and now it has half of the substrate protein stuck to it. We have to restore the enzyme to what it was before. We must recycle it. So the rest of the enzymatic mechanism is dedicated to doing just that, restoring the active site back to where it was. We need water to come into the active site at this point for a deacetylation reaction. Of course, the enzyme is floating in a bag of water. It's present in the cell. It's present in the small intestine. We are nothing but bags of water, so water is everywhere. And a water molecule happens to float into the active site. That water molecule is held in place through a hydrogen bond between this histine nitrogen and one of the protons of water. And this oxygen of this water molecule is going to be an attacking nucleophile. And my heart's starting to break. I don't know about yours, because what do you think that oxygen of that water molecule is going to attack? What is it going to beat up on? The same damn poor carbonyl carbon that we've been beating up on all mechanism. So the oxygen of this water molecule launches a nucleophilic attack on that same carbonyl carbon and wins that attack, makes that bond. Oxygen, of course, can only have 2 bonds at any one time, and if this oxygen just made a new bond with this carbonyl carbon, it has to let go of a proton. And it lets go of this proton back to histidine. Histidine is our proton repository. Keep in mind, histidine just acted as a base, or a proton acceptor. Because this carbonyl carbon is making 4 bonds now, it had to, yet again, steal one of the 2 bonds of its double bond here with this oxygen in order to make that 4th bond here. This oxygen is once again reverted to being negatively charged, and it is once again unhappy. And it's going to launch its own attack to get its double bond back. When it launches that next attack, and it gets that double bond back from the carbonyl carbon, the only bond that the carbonyl carbon can now break is the bond that was holding it to serine. And so we have severed the connection of the second half of the substrate molecule with the serine of the active site. This half of the substrate is now free of the active site side chains, and it can float out of the active site. Because the oxygen of serine lost its second bond, it's hungry for its own second bond, and luckily for it, histidine 57 was holding on to a convenient proton that it, histidine 57, could donate back to serine to restore that hydroxyl group. In this case, histidine is acting once again as an acid, giving a proton up to serine. If you take note of it, we've regenerated the enzyme. Serine is back to being its old self with a hydroxy group. Histidine is back to being its old self with a free nitrogen there. And as soon as that half of the substrate clears the active site, we will have an empty active site that can repeat this process yet again. The only thing that's really different in this whole enzyme at this point is the hydrogen in red that you see on the screen that serine is now holding on to. That hydrogen came from the water molecule that entered the active site in phase 2 of the mechanism. The rest of the enzyme is entirely the same. The reason we needed that hydrogen from water is the original hydrogen we started with, that serine initially donated to histidine, histidine then gave to the leaving group, to the amino group of the half of substrate that left as a leaving group in phase 1. So again, this is the ideal example of an overall enzymatic mechanism. This is a simple enzymatic mechanism, air quotes yet again. I fully appreciate that a whole lot of chemistry just occurred before your eyes, but trust me when I say there is no enzymatic mechanism that I'm aware of that is simpler than this one. So when we say this is a simple enzymatic mechanism, we mean that in a very relative sense. This is the simplest enzymatic mechanism we know of, but still there's a great deal of complexity, detail, and biochemistry that's occurring. We won't be discussing any more biochemical mechanisms in this course, obviously, because they take a lot of time and they're quite complex, but hopefully you have a good idea now of how catalysis actually happens and how enzymes can accomplish the jobs that they do. Essentially, for cleavage reactions such as this one, what occurs in the active site is part of the enzyme pulls really hard on one side of the substrate, and another part of the enzyme pulls really hard on the other side of the substrate, and both those halves pull and pull and pull until the covalent bond under attack cracks under that stress, and we essentially achieve the cleavage that we needed. Because covalent bonds are nothing more than shared electrons, really what we're pulling on are those electrons and the energy that they store. So let's broaden our scope a little bit here and talk about chemical reactions in general that we tend to see in enzymatic mechanisms. As you just saw, enzymatic mechanisms are fairly involved, dense, and complicated things. But surprisingly, enzymes have a fairly limited number of tricks up their sleeve that they can do. We call these tricks, quote unquote, types of chemical reactions, and we classify them as such. Of course, the exact substrates that are experiencing these reactions and the enzymes that are performing them differ, but what the enzymes can do is largely the same across all enzymes. One of these common reaction types are nucleophilic substitutions, and we just saw a nucleophilic substitution or a nucleophilic attack a moment ago. The general reaction for any nucleophilic attack is that some attacking nucleophile R is bound to some group X, but it would rather be bound to Z, and so it attacks Z and lets go of X. So to put this in the context of the chymotrypsin mechanism we just witnessed, we can think of Z as the attacking nucleophile. That would mean that Z is the oxygen of the serine side chain. R is the carbonyl carbon, and X is the other side of that peptide bond, the amino group of the second half of the substrate molecule. The two dots here, of course, represent the covalent bond of shared electrons, and we can think of this as the peptide bond in the substrate we just observed. So the attacking nucleophile, the oxygen of serine, attacks its substrate, and in this case that was the carbonyl carbon, and makes a bond with it. Because that bond is made, the bond with the second half of the substrate, that peptide bond itself, the bond to the amino group of the rest of the protein, is cleaved, and the rest of the protein was released as a leaving group. So in this general example, Z is the attacking nucleophile, again the oxygen of serine in our previous example. It's hungry for an electron-deficient atom, and X is the leaving group, what leaves as a result of the reaction, and in the case of chymotrypsin, that was the second half of the substrate molecule, everything that lied after the peptide bond that we cleaved. In biochemicals, the carbons of carbonyl carbons are often the targets of nucleophilic attacks. We saw that as well. Those carbons are very electron deficient. The double bond with oxygen is stealing a lot of electrons, and so they make an easy target. They're easy prey. Common biochemical nucleophiles that launch attacks are oxygens of serines, as we saw, also the oxygens of hydroxyl groups of threonine and tyrosine as well. Another common biochemical reaction that we typically see in enzymes is what's referred to as general acid-base catalysis. Remember, acids are proton donors and bases are proton acceptors, and in acid-base catalysis we see the donation and acceptance of protons. So these types of enzymatic reactions revolve around the release and acceptance of protons. When we release protons, we're breaking bonds. When we accept protons, we're making bonds. And the point of the reaction in this case is always the shuttling or moving of covalent bonds from one place to another. If the enzyme donates a proton, we'll just say that general acid catalysis is observed. If the enzyme accepts a proton, we say that general base catalysis is occurring. And in the case of chymotrypsin, we saw both. We saw true general acid-base catalysis, where histidine was operating as both a proton donor and a proton acceptor as needed. In fact, histidine is the only amino acid that can act as an acid and a base simultaneously in a single reaction mechanism, and that's because histidine has a pKa near physiological pH. With its pKa near 7, histidine can act as a proton donor or acceptor on demand, and we talked about that very early in the course when we went over acids, bases, and buffers. So these two reaction types go hand in hand. Acids can be thought of as electrophiles, bases can be thought of as nucleophiles, and so when we give up a proton, we've created something that's hungry for a new bond and it's reactive. When we've accepted a proton, we've satisfied a reactive group and made it quiet. So we can control the reactivity and the attacks that we observe by stealing and giving protons respectively. Regardless of the reaction type, all enzymes have an additional characteristic that we've also hinted at already called substrate specificity. Specificity is the idea of binding to and acting on only one type of substrate. Absolute specificity is when an enzyme will work on and bind to, catalyze, only one specific substrate molecule, one thing and one thing only. These enzymes with absolute specificity have fairly rigid, stringent active sites. They're more lock and key than induced fit, and so they can only bind a precise and specific substrate. Relative specificity is when an enzyme does a reaction, but it can do that reaction on a fairly larger, more varied and diverse group of related substrate molecules. Chymotrypsin, for example, shows relative specificity. It can cut the peptide bond on almost any protein as long as that peptide bond lies adjacent to a large and bulky nonpolar hydrophobic amino acid. If chymotrypsin had absolute specificity, it would bind to and cut the peptide bond of one protein and one protein only. Doesn't make sense for a digestive enzyme. We eat all different kinds of proteins and we need to digest all different kinds of proteins. So chymotrypsin can bind to many of those proteins and cut their peptide bonds. That's relative specificity. Enzymes with relative specificity have a more relaxed and flexible active site, more conforming to the induced fit model. Interestingly, some enzymes can also have what's called stereospecificity. Stereospecificity is when an enzyme can distinguish between chiral molecules, can distinguish between non-superimposable mirror images. So only the molecule with this particular orientation can fit into the active site. And if this group B was over here and this group A was over here, then that molecule would not fit in the active site. This is a higher level of absolute specificity. Let's wrap this chunk up with a brief discussion of coenzymes. Enzymes are amazing, and I really genuinely hope that all of you are beginning to get an appreciation for just how fascinating and amazing enzymes are. They are, without a doubt, the titans of life. Life would not be possible without enzymes. But like most superheroes, they can't work alone. Every Batman needs their Robin. And so enzymes need to have a helping hand oftentimes to perform catalysis. Enzymes often require cofactors for their catalysis, and cofactors are largely considered to be non-protein molecules that are aiding in and taking part in enzymatic reactions. And we break cofactors up into two broad classes. Metal ions, which are self-explanatory. We'll see metal ions involved in the catalysis of biochemistry again and again as we go deeper into this course. And the second class are coenzymes. Coenzymes are their own mixed bag, a hugely diverse mix of organic compounds. Biotin is an example of a coenzyme. Flavins are coenzymes that we'll see near the end of the course. They are involved in holding on to electrons. Thiamine is a coenzyme. Niacin is another electron holder that we see. Nicotinamide is the primary component of a molecule called NAD, and niacin is what a cell uses to make nicotinamide. And we're going to see probably in about 6 weeks that we would not be alive without NAD. NAD is one of the most important molecules in our bodies. So these are a few examples of coenzymes that are critical for life. And I should say that biotin is a methyl group holder. So when we make biomolecules, when we synthesize new amino acids or nitrogenous bases, oftentimes we have to shuttle methyl groups around, and that's what biotin is for. Some of these names might sound familiar to you and not from class. If you take a look at the back label of any multivitamin that's out there, you'll see thiamine, you'll see flavin, you'll see niacin, and for some of them, you'll even see biotin. Vitamins are really nothing more than coenzyme pills. When we take vitamins, we're taking small molecules that our enzymes need to perform their jobs properly. Most of these molecules are present in a well-balanced diet, but so few of our diets are well-balanced anymore that we now take these multivitamins to kind of make up the difference. Vitamins are not nutritious. Vitamins do not provide energy. Vitamins are not food. Vitamins are capsules of coenzymes that allow our bodies to digest the foods we eat with a great deal of efficiency, giving us the energy we need to survive. And let's not stop at biotins, flavins, and niacin. The other class of cofactors that enzymes need in order to be functional are metal ions. And metal ions are calcium, phosphorus, magnesium, copper, manganese. All of these are metal ions. So again, vitamins are really cofactor pills. Sorry about that telephone ring there. That's the dangers of recording in one's office. So what do metal ions do? Well, they do a lot of different things, but one of the things that metal ions do, we actually talked about in this course a couple lectures ago as well. Sometimes if two negatively charged side chains are in close proximity to one another in a protein, they would normally repel one another. But if the protein needs to stay in that three-dimensional shape, it has to somehow neutralize and ideally hold those negative charges close together. Metal ions will do that. Most metal ions have a positive 2 charge, and so metal ions can interact with two negative side chains simultaneously and attract those two side chains to themselves, to the metal ion, to some central point, bridging those negatively charged groups together. Vitamins in particular often participate in redox reactions. When we get to redox reactions in this course, in about 3 more lectures or so, we'll see that redox reactions are nothing more than the transfer of electrons. Some of you might know that from previous courses. And so many of these coenzymes, especially niacin, NAD, and flavins, FAD, are important in electron shuttling. Electron shuttling is ginormously important for metabolism and making ATP. B6 vitamins become coenzymes when they're phosphorylated. They tend to be involved in the transfer of amino groups from one molecule to another. This is important in making amino acids and clearing nitrogen waste. So to suffice it to say, without coenzymes, and more broadly, metal ions too, cofactors in general, many enzymes would not be able to do their jobs at all or do them as efficiently. So in many ways, cofactors really are Robin. They really are the unsung heroes of the enzymatic reactions and metabolism that occurs in our bodies. So to summarize this lecture chunk, I mean, here it is, man. This is really all we have to say about most of what we talked about. The enzymatic mechanism of chymotrypsin. Know this enzymatic mechanism well. I hold each and every one of you responsible for understanding this mechanism step by step and knowing how it works. To summarize it briefly, in step 1, the oxygen of serine launches a nucleophilic attack on this carbonyl carbon and bonds to it. That new bond creates a scenario where the carbonyl oxygen has to let go of one of its 2 double bonds, and that makes it negative. This negatively charged oxygen is unhappy and launches an attack of its own, stealing its double bond back, but in order to accommodate that, the peptide bond on the other side of this carbon is broken. This nitrogen requires 3 bonds to be content. Its 3rd bond comes through the donation of a proton from histidine 57. That proton that this nitrogen gained is the proton lost by serine 195. This half of the substrate protein leaves as a leaving group. To regenerate the molecule, to regenerate the active site, water floats in. Water launches its own nucleophilic attack on that same carbonyl carbon. Simultaneously, this oxygen makes a bond with this carbonyl carbon while it lets go of this proton to histidine 57. We see that new bond between the oxygen of water and the carbonyl carbon made here. That bond is accommodated by the loss of the second bond with this same oxygen. Histidine is holding on to water's proton. This negatively charged oxygen is unhappy once again. It launches an attack on the carbonyl carbon to regain its double bond. It wins that attack, and to accommodate that double bond, the carbonyl carbon breaks the bond that's holding it to serine 195. This half of the substrate protein is now free and can leave as a leaving group. The last step that remains is the satisfaction of the oxygen of serine 195, and that comes through the donation of water's proton from histidine 57 to that serine oxygen, restoring that hydroxyl group. Whew! That is your chymotrypsin enzymatic mechanism, and there is a more informal online tutorial for that mechanism available on YouTube as well. Whoops. We also spoke a little bit about the classes of enzymatic reactions that we see: general acid-base catalysis, nucleophilic attacks, and the like. Chymotrypsin is a wonderful example because we see a lot of those types of reactions in action in order to break that peptide bond and regenerate the enzyme. We ended the lecture with a discussion of cofactors, metal ions, and coenzymes. These are the small, inorganic in the case of metal ions, or organic in the case of coenzymes, these small biomolecules that aid enzymes in doing their catalysis, and we'll see cofactors crop up more and more as we talk about specific enzymes in their role in metabolism. That's the end of the Lecture 7 series. I hope you enjoyed it, and I'll see you on the flip side at the beginning of Lecture 8.